In the capital of Malaysia, a record-breaking skyscraper has risen right in the heart of the historic urban core. Merdeka 118, the second tallest building in the world after Burj Khalifa. With a height of 678.9 meters and a total investment of about 1.5 billion US dollars. This is not simply a large-scale construction project. It is a strategic statement about Malaysia's ambition, position, and future on the map of 21st century global megacities. So how were people able to build a tower nearly 700 meters tall, right in a dense city center, on complex and high-risk geological ground? In this video, join Mandarin Tech as we explore how Malaysia built the second tallest building in the world and turned it into a new symbol of power for Southeast Asia for decades to come. Located right next to Stadium Merdeka, the site that marks the birth of modern Malaysia in 1957, Merdeka 118 was built as a symbol of the country's next stage of development in the 21st century. This skyscraper was designed by architect Carl Fender and fully funded by Permodalan Nasional Berhad, a state-owned enterprise of the Malaysian government. With more than 118 above-ground floors and a height of nearly 679 meters, the tower was designed not only as an architectural landmark, but also as the core of a large-scale urban complex, including financial offices, a luxury hotel, a shopping center, and modern public spaces. Highlighted by a multi-level atrium space rising 36 floors and organized as a vertical activity core inside the tower. The glass facade of the tower is shaped like multifaceted crystal forms inspired by traditional songket patterns, reflecting the diversity and intangible cultural heritage of Malaysia. The tower's spire, rising approximately 160 meters, further recreates the iconic image of Malaysia's first prime minister as he raised his hand and shouted Merdeka at the historic moment of independence. The name Merdeka itself also means independence in English, directly linking the structure to the founding memory of Malaysia. At the same time, the project is directly connected to Merdeka MRT station, integrating the entire complex into Kuala Lumpur's modern urban transportation network. Construction began in 2014, with approximately 100,000 tons of earth excavated. The central area of Kuala Lumpur where the tower is built has extremely complex geology, consisting mainly of limestone, with numerous voids and underground caverns. This makes the ground unstable and poses a significant risk of settlement if not handled with precision. To address this, engineers implemented one of the most complex foundation systems ever constructed in Malaysia. First, trench cutters were used to create a trench nearly 1 meter thick in a circular shape with a diameter of approximately 80 meters, which was then filled with concrete to form a retaining wall surrounding the construction site. This was followed by the installation of 137 board piles, each drilled more than 60 meters deep into the ground to transfer the enormous load of the tower into the underlying strata. After completing the piling system, excavators dug down to expose the pile heads. These were then connected using reinforced steel and covered with approximately 45,000 tons of concrete to form a solid foundation capable of supporting the massive structure above. This process ran continuously for dozens of hours, requiring absolute precision and coordination. At the same time, the top-down construction method was applied, allowing excavation and structural construction to proceed simultaneously from the top downward to complete the 5-level basement deep underground. Finally, a protective structural layer was completed to secure and safeguard the entire foundation system. After completing the foundation, the next challenge was constructing the structural system for the 118-story building. The construction process began with casting the central core using a large mechanical formwork system. This core is surrounded by 8 massive reinforced concrete columns, forming the primary load-bearing frame. The entire structure is then connected together by robust steel structural systems. At the top of the tower, 4 large cranes were installed to support the construction process. From here, These giant cranes continuously lifted materials to each floor, maintaining a steady construction rhythm as the skyscraper gradually rose over time. However, as the building grew taller, the available working space became increasingly limited, posing challenges to construction progress. To address this issue, engineers utilized a formwork system. Workers assembled the formwork using wooden panels and poured concrete to form each level of the core. Once the concrete hardened, the formwork was removed and the entire system was lifted upward using hydraulic mechanisms along rails attached to the core structure. The Spire section of Merdeka 118 was constructed in a completely different way compared to the main structure of the building. Instead of being built as a single complete form, the entire spire structure was fabricated into multiple separate steel modules on the ground, which were then gradually lifted and installed at their final position. These modules were raised using a dedicated hydraulic jacking system, allowing individual components weighing tens of tons to be lifted to heights of hundreds of meters with extremely precise control. Once in position, they were aligned and fixed to the main structure of the tower, forming a complete integrated system. This installation process required close coordination between lifting equipment, measurement systems, and the engineering team, as each component had to fit precisely within the overall design. When the final module was installed, Merdeka 118 officially reached its maximum height of 678.9 meters, marking the completion of the structural form and making the tower one of the tallest buildings in the world. After the spire reached its maximum height, the project did not immediately enter a completed state. Instead, another equally important phase began: the completion of the external building envelope. Thousands of facade glass panels were installed in small modules, precisely attached to the predefined steel frame structure. Each panel had to be accurately aligned to match the curvature and tapering geometry as the tower rises. At heights of hundreds of meters, strong winds and structural vibrations made installation extremely difficult to control. As a result, the entire process relied on laser measurement systems and temporary suspended platforms to ensure near-zero tolerance. Alongside the external envelope, a complex internal technical system was developed simultaneously. The entire network of electricity, water supply and drainage, central air conditioning and fire protection systems was divided into zones based on building height rather than operating as a single unified system. This zoning allows the tower to adapt to changes in air pressure, temperature, and wind conditions at different levels, a critical requirement for super tall buildings. One of the key components is the high-speed elevator system of Merdeka 118, designed with a zone configuration and connected through sky lobbies to optimize internal traffic flow. The system is capable of serving approximately 15,000 people per day, while significantly reducing travel time between lower and upper floors. Integrating the elevators into the core structure required absolute synchronization with the core construction, ensuring stable and reliable overall operation. Before operation, the building undergoes a final testing and calibration phase. All structural and technical systems are tested under near-real conditions to ensure long-term operational stability. Once all components are confirmed to meet requirements, Merdeka 118 officially enters its operational state. With no more cranes or scaffolding present, the tower transforms into a vertical urban structure where offices, hotels, retail spaces, and public areas coexist within a unified system. From a massive construction site in the heart of Kuala Lumpur, the project has now become a fully completed architectural landmark, marking the end of its construction journey and the beginning of a long-term operational cycle as one of the tallest buildings in the world. Merdeka 118 is not only a skyscraper in terms of height, but also a clear statement of Malaysia's organizational capability, engineering strength, and urban ambition in the 21st century. Moving beyond the concept of a tall building, the project becomes a symbolic structure where architecture, infrastructure, and technology are integrated into a unified system. From a plot of land with complex geological conditions, through multiple challenges in foundation work, structural construction, construction constraints, and even social context, Merdeka 118 gradually took shape as an accumulation of large-scale construction capability. Each phase not only addressed technical problems, but also reflected the maturity of modern urban construction. More importantly, Merdeka 118 carries historical symbolic value, as the name Merdeka recalls the spirit of independence in the nation's transformation. The project therefore serves not only commercial or architectural purposes, but also stands as a milestone representing the confidence of a rapidly developing economy ready to participate in the global infrastructure race. So are you curious about how the tallest building in the world, Burj Khalifa, was built? To ensure the tower would not only exist but become the centerpiece of an entirely new city, Dubai launched a construction plan of unprecedented scale. More than 12,000 workers from over 100 countries worked in shifts around the clock. The Burj Khalifa emerged as a powerful declaration. Dubai would not simply survive the post-oil era, it would shape its future with intelligence, ambition, and world-class engineering. For a structure like the Burj Khalifa to stand on its own, simply scaling up the design of conventional high-rise buildings was impossible. The engineering team had to create an entirely new foundation system, one strong enough to support a structure weighing more than 500,000 tons on the weak desert soil. With no bedrock to anchor into, they designed a massive raft foundation, 12 feet thick, buried 24 feet deep, and covering 80,000 square feet. The raft foundation acts like a large board that spreads the entire load over a wide area, reducing pressure on the soft soil beneath. Just as flat-soled shoes do not sink into grass while high heels dig deep, the raft foundation helps the tower remain stable even without solid rock to rely on. Even though the raft foundation distributes load very effectively, it still needed to be anchored firmly to resist lateral movement caused by wind and soil deformation. Therefore, the engineers added a friction pile system consisting of 194 concrete piles, each 5 feet in diameter, and drilled to a depth of 164 feet. The remarkable thing is that these piles do not reach bedrock because the area has no solid rock layer at an appropriate depth. They rely entirely on friction between the pile surfaces and the weak sedimentary soil to stabilize the entire structure. Although each pile does not provide immense resistance individually, the combined effect of hundreds of them creates extraordinary lateral strength, sufficient to secure a tower weighing more than 500,000 tons. Settlement measurements after completion were only about 40 to 50 millimeters, an impressive figure for the tallest building in the world, proving that the foundation system performed exactly as designed. The next challenge lay in building a structure more than half a mile tall using cast-in-place concrete. As the tower continued to rise, the biggest problem emerged: how to pump concrete to nearly 1,965 feet, a height that had never been achieved before. At this level, the concrete would remain inside the pipe for more than half an hour, long enough for it to begin setting and potentially ruin the entire system. To solve this, the engineers developed a special concrete mixture with admixtures that preserved workability for an extended period. The concrete was mixed with ice water to reduce its temperature and pumped only at night to avoid the outdoor heat above 104 degrees Celsius, which would cause the material to harden too quickly. The world's most powerful Putzmeister pumps were deployed, capable of pushing concrete nearly 1,965 feet in a single pumping operation, setting a new record in the construction of super-tall buildings. Parallel to the challenge of pumping concrete, the engineers faced another issue. The central concrete core became too slender as the height increased dramatically. The solution was inspired by ancient Gothic architecture, where buttress walls were used to stabilize cathedral structures. The Burj Khalifa applies this principle by adding 3 large buttresses radiating from the central core, forming its distinctive Y-shaped plan. These 3 wings distribute compressive forces across the entire raft foundation, reduce torsion, and enhance wind resistance. This was the first time a 3-buttress structural system had ever been used for a skyscraper, and it became the fundamental reason why the Burj Khalifa could continue rising while maintaining the stability it needed. As the tower rose into the sky, the working environment became extremely dangerous. Workers were transported to higher floors using steel cages that moved along the structure. Even so, a small number of workers lost their lives during construction. Even after the building was completed, those responsible for maintenance, such as the rope-suspended window cleaning crews, still had to face unpredictable risks. They hang themselves by 3 ropes in midair, working in strong winds that can reach more than 19 knots. When the wind exceeds the permitted limit, all work must stop immediately to ensure safety. Cleaning the entire glass facade of the tower takes up to 3 months, and all of it is done manually, mostly by workers from Nepal, where mountain climbing is almost a tradition. A silent but crucial component is the series of mechanical floors. These mechanical floors are the backbone that helps the entire building stand firm against storms and its own enormous weight. These are special technical levels arranged intermittently along the tower and can be identified by the dark bands on the exterior. Inside, they function as rigid planes, connecting the forest of concrete steel columns with the hexagonal central core, helping to distribute wind forces, reduce torsion, and prevent the structure from bending. These floors also house electrical systems, water tanks, and essential technical equipment, while providing anchor points for the facade cleaning teams. By 2008, when the Burj Khalifa had already surpassed every record and become the tallest structure in the world, one part was still unfinished: the metal spire more than 700 feet tall. The problem was that no crane on Earth was tall enough to install it from the outside. Therefore, the engineers chose an unconventional solution: assembling the entire spire inside the tower. They built each segment of the spire right within the hollow space of the building, then used a jacking system to push it upward, gradually along the vertical axis. When the final metal tip pierced through the top, the Burj Khalifa reached its ultimate height, 2,717 feet. No structure on the planet even comes close to this height. When you look at the entire city of Dubai below, you will understand that you are witnessing one of the greatest engineering feats in human history. At a certain point, every structure becomes a thing of the past. But Burj Khalifa is different. It becomes a standard. From the foundation driven into desert sand to the final meters of the spire, every detail of this building tells the same story. Humans didn't just build a tower, they built their own capability. And it is the willingness to do what no one else dared to imagine that turned Burj Khalifa from a bold blueprint into an engineering icon of the modern world. It reminds us that limits exist only until someone surpasses them. If you want to continue exploring the great structures that have changed engineering and the face of the world, don't forget to like and subscribe so you won't miss any journey with Mandarin Tech.